Thank you. So, hello everyone. Thank you for the opportunity to talk today to Iteration 2022. Yeah, maybe a few words. I'm an engineer. I'm half German, half Italian, half French. I love the things that are rationalized. I did product development all my life. And I would like to tell you a little story that happened to us as we received the tubes in Francazal. Francazal is located very close to Toulouse in France, southern France. And there we have built and continue to extend a test track that is full scale to test all the technologies of the Hyperloop. I will tell you a bit more about it. And we started with very simple tubes. It's a technology that comes from the gas and oil industry. So very, very simple, as you can imagine. We were trying to get inspired by everything that exists. So this is exactly our tubes. And what happened is that when they came, so we were expecting just a few tubes. I mean, it's just steel tubes. And that created a complete amazement. The people became crazy, and even very rational people, the German engineers like I am, were completely impressed by their steel tubes. And the story is about the product vision and the marketing. And I have now a running joke with my friends that we have a fantastic marketing department, and my running joke is I'm applying to work with them now. It's to say that with bare tubes here, that's the engineering work, and this is here what the people and even engineers, other engineers have seen thanks to the effort of the marketing and the communication. And it was funny for me to see the discrepancy between the amazement of simple engineers on bare tubes and thanks to this work on how we communicate about the product vision, in our case, the Hyperloop, this is what you get people to see, even though they just see a few pieces of steel. And this is something that have struck me, and that guides also my work today to help the engineers continue developing the Hyperloop. But before we go there, I would like to tell you, to present you quickly what a Hyperloop is. So basically, the principle of a Hyperloop is the principle of a tube. It's you take so those tubes that we saw earlier, you remove the first source of energy consumption, which is the air, okay? And the other advantage of the tube is not just the reduction of energy consumption, is also that you are in a fully controlled environment, meaning that you know at every point in time and space what is there, what is the temperature, what is physically there is continuously monitored. And so it's probably the only mode of transportation which is in an environment that is fully controlled. And this has some very important points, such as the fact that it needs to be safe. So it's our primary focus, it's the safety. And this control environment allows us to have a simpler architecture of the system. Or that's our daily challenge, is to keep it simple, at least. And with this, we hope to be able to demonstrate the safety in a reasonable time frame. As you know, railways, aircrafts, cars, they had 100 years, sometimes even more, to demonstrate their safety. And today, safety has been reached in small steps. We will have to meet the highest level of safety right away. For this, the fact that we're in a controlled environment with a simpler architecture is fundamental to the concept of the Hyperloop. Another point, so we talked about the low energy consumption, we talked about the environment control. Another feature is the speed. It's a ground infrastructure, and we see that the market has put us in a place where we have no choice as being fast. So everything below 600 kilometers per hour will be allocated to railways. So even though we do not see Hyperloop TT really as a competitor to railway, we have to position the speed higher than 600, which is something that we think is really doable. So 600, 900, and up to 1200. At some point, you are limited simply by the application case. So when you are very fast, you cannot do good curves, and you increase the cost of implementing the Hyperloop. A last point on the Hyperloop product. We were speaking about the railway. The railway has a very strong focus on capacity, for example. This is the paradigm offered by the railways to offer big capacity. The paradigm of Hyperloop is a little bit different. Even though the capacity can be pretty interesting, the focus of the Hyperloop is really the profitability. So we aim at having a system that can pay for itself. So a profitable system that will allow for private financing of the infrastructure. So this is a few words on the Hyperloop, just to explain you what we are talking. So it's a transportation system. As such, it's pretty ambitious because you need all the resources allocated to the demonstration of safety. But not just this, we just talk about profitability, and there the cost target we have both for the deployment, so in terms of CapEx, but also in terms of OpEx, are pretty tight. And so we need to put good effort there to meet our targets. We will be ready to build a Hyperloop today. We will know how to build it, but it will not be safe and it will cost too much. So we still have a little bit of work to do to demonstrate the safety in the first place, and also the cost targets are met. It's also even a little bit complicated than what I just said. We are having not just one product actually, but we are having several products. Unfortunately, I would prefer to have only one product, but we need several products. We think that for the demonstration of the safety, especially, we will need an intermediate steps that we will combine with an industrial demonstrator. And so we will have several iterations. So our first aim is to deliver a semi-commercial prototype that has all the functionalities, that is certified to allow for the welcoming of public passengers before we go to a full capacity and full length product. We also have other products to live with. For example, here in Francazal, we have a 320-meter test track. It's very close to a final product, actually. So this one had to be developed, and we had other test benches that we need to develop too. So what I'm trying to say is, on one hand, we have a simple architecture that makes our life hopefully where we hopefully will be able to keep things as easy and simple as possible. But on the other hand, we need to go through several steps before we deploy a full commercial route. And this, of course, increases the complexity. Maybe a few additional words for you to understand our context. So we are a startup. We are privately financed mostly. We have here and there a little bit of subsidies, but mostly we are privately financed. And so we need to, on one hand, to be as fast as possible. On the other hand, we depend also on the means that are available. Meaning sometimes we have acceleration, sometimes we have deceleration, and in any case, you have never enough time. You never have enough people, and you never have enough money. But I think this is very common to many participants here in the attendance. So just to draw a little, just a few words on this context. What we are doing these days is a lot of tests too, to give you a little bit more flavor. We are testing vacuum, we are testing the linear motor, we are testing capsule systems and components, we are testing systems controls quite a lot. Those tests are also very expensive because of the reason I explained before, that we need to be fast. We like to shoot for scale 1 as fast as we can, and I think we are ready to test everything at scale 1. Independently, it's nearly done. Now we are in the phase where we integrate all the systems together and test them together. And this is very resource consuming and time consuming, much more than when you're doing low scale test. But it's the time. Low scale test is of course more safe, but will take much more time, and hence money. At the end of the time, it's always a question of money. So maybe a bit about the role of the programs here. We have a system that has, at the end of the day, many customers. Of course, you have the passengers. You will have the consortium that will build it on every country. You will have the country, the regions, the cities. You will have the industrial partners that will contribute to the construction of the Hyperloop. So you have a full ecosystem of customer in a wide meaning. And at the end of the day, you have one product, which is the system. And so this involves, of course, finance. It involves passenger experience. It involves, of course, a lot of engineering. It involves procurement, supply chain, and all the regulatory and certification interlocutors. So we are in a world where you have strong, let's say, domains. When you're doing, I would say, small products, then usually you have a product director or product manager. In our case, we took the standard, organizational standard of you have in the aerospace and also a little bit in the railway, is the program to coordinate in transversal the activities of all those departments. And so the role of the program, my role, which Stefan asked me to present a little bit, is to help all the different teams working on the same products. You must all have had that experience that when you're asking one team, they will present you the product in one way. When you ask another team, they will present you the product in another way. And we need to make sure that everyone talks about the same product. For such a project and for such a development, this is a key a key goal to be not only achieved but sustained over time. In terms of development methods, I know that with Valley Space and the teams, you are pushing the boundaries of systems engineering to the maximum. In our case, we try to at least use existing methods. So the product and the system at the end is the innovation. The individual technologies are not necessarily the innovation, with a few notable exceptions, such as the propulsion. But we are trying to use off-the-shelf technologies. We are trying to use also off-the-shelf development method and to not reinvent the wheel. The holy grail in this, of course, because it's a new system and a new product, we too have requirements and moving targets. So the holy grail is to be capable to have a little bit of agility. So we do the classic system engineering, we do the classic project planning, but we try to introduce a little bit of agility with some success. For example, what we now do is to plan long-term very roughly. So we still have the full V-cycle planning and the overview on the timeline, but we try to not go too much into the details. And the more we close on today, and especially for the next 3 to 6 months, we try to have a very detailed plan where everyone knows what he should be working on. So we kind of transpose the agile world that many of you know from the IT, where the sprints duration are 1, 2, or 3 weeks. For us, it's more 1, 2, or 3 months. But we have some success with that, in that we adjust the project management effort and project planification effort to the granularity we need. And also in that we can readjust for many systems when we have those moving targets effect. So it's hopefully not too theoretical. Okay, another topic I wanted to offer here as a practical example of what we do to simplify a little bit our world. On one hand, I said we try to implement all the classical product development approaches. On the other hand, if we do it by the books, then everything will become way too complicated. And one thing the aerospace has successfully done is this ATA 100 system. So I don't know, for the one that are not from the aerospace, it's basically like a systems breakdown structure. It's not a perfect one. It has a lot of imperfection, but it's a breakdown. Let's put it away. It's a system breakdown that where engineers can work with, procurement can work with, finance can work with, many different departments can work with the same product breakdown structure, meaning that ideally purchasing has its own hierarchies, engineering has its own hierarchies, and sales and manufacturing, everyone has his own hierarchies. This is nice, but when you need to discuss electrical systems, when you need to discuss a door, when you need to discuss a tube, if the hierarchies do not match, are not coherent, one which is each other, it becomes quickly very difficult. And in a context of very constrained resources, such as the one of a startup like ours, we are always very constrained. It becomes critical, and we cannot afford to have 2,000 people giving us the transposition from one hierarchy or product breakdown structure to another one. So this is what this ATA100 allows for, is to have some commonalities in the hierarchies on how we describe the products from those different perspectives, so that we can quickly discuss on a scope that is not right away the full system scope. And this is something that has proven being extremely useful. So we have reinvented the ATA 100 for the Hyperloop. This is something very useful, which I can recommend, especially for those products. We have 300,000 parts, roughly, more or less. So this gives you an idea where you can use these kinds of approach. Another good thing with this standard high-level breakdown structure is that we can allocate the effort of everyone. Today, we are not manufacturing anything, we are not selling anything, so we do not have any operations for now. We are just doing projects, development projects, and we can allocate the development projects to every sub-part, we call them product element, so that for product element you can see if you have put the right level of effort, or if you should be reprioritizing the effort of the different teams there. Exactly. So here I can come back to give you some of the things we are talking, especially for the Hyperloop. Here you see our fully developed pump unit. It's in a container to allow for quick installation and quick manufacturing. We know it's too expensive, and it requires too much energy, but the energy consumption of this is so low, and the cost of this is so low, so negligible, that we don't care. So we are in a situation where we need to cut a little bit in the turns. And when we have something that is working very well, here we had better results in our test than what we had simulated and modeled. Then we can validate, and we go to the next subsystem. One of the next subsystem here, you see the first part is, for example, the valve, which we will have, and which allow to handle some specific scenario, to close airtightly the tube. This is another example here of what we have achieved. We are implementing our operations controls right away for our test benches. So in Francazal, we have a test bench. So it's not a prototype per se, but our approach is everything digital and interface. Every time we can do it as close as possible to the end product, we do, and we test it right away on the test bench. This is extremely powerful, and it's very easy to do, especially with the systems control, because you do not need also sometimes all the hardware. You can simulate some other subsystems. So it's extremely powerful, and it help us to increase the maturity in our system design much faster. This is the, you see in the behind, and everyone is welcome to come see, visit us in Francazal. Here you see the tube we have installed on 320 meter, and you see a senior executive of the USDOT visiting us and on the safety demonstration. So safety for us has always been the highest focus, and we have started with safety. So 4 years ago, we have defined a safety baseline because we have no certification baseline for the Hyperloop. So we had to develop one, and we are now in advanced discussions since 4 years with the USDOT and the European Commission to advance and to validate this baseline as we progress. This is some rendering of our capsule interior too that I wanted to share with you. I must do that quickly. And this is the capsule we have developed. Also here, we know it's good enough to begin, but because we have developed it very close to what will be at least our first commercial Hyperloop, we also see now everything that can be improved. So we have this logic that it's okay to develop something that is not perfect, as long as it's not too far from our goals in terms of cost and environmental impact, energy consumption. The only part where we can never do compromise is safety, of course. But here we have a capsule that will work, but that's where we know where the generation 2, we have a lot of idea for generation 2 and 3 on how to improve it already. So I just wanted to give you a little overview, a little behind the scene overview on what is happening to develop such a system through a startup like ours.
Thank you very much, and we all wish that you could be here. Before we open up the floor, I have one question, and that's I guess your project is one that I imagine requires the approval of city planning councils and other bureaucratic obstacles that you need to overcome long before any construction can begin. Now, how is this factored into your design process and also company infrastructure challenges like fundraising and other things like this?
Yeah, it's a very good question. So, as I told earlier, our preferred way is to build a demonstrator, a full prototype, so as close as possible of our end product, of course, but on a limited length. So the ideal length probably will be for engineers 20 kilometers. What we have discussed so far is lengths between 5 and 10 kilometers. We have very specific opportunities there. And when you are discussing those lengths, then you can find places on the planet. We have several options right now to deploy such track. You always have constraints, but they are largely reduced. Okay, and then what we also see, we have done several feasibility studies around the world. There is a pretty large list now of route opportunities, of which quite a few now that are well identified, and in some areas. You always have an environmental concern. This is growing all over the planet, and it's very aligned also with the goals of the systems that we are developing. But you have places where this can go faster, and probably the first Hyperloop definitely won't be in the United States and or in Europe, at least a long one, a very long one, because of the points you mentioned. There is no shortcuts here, and but demonstrator, you definitely have the room, or for a small Hyperloop in the United States or in Europe. Yeah.
Just quickly, where do you
but basically, to answer to your question, we try to, of course, just avoid to have too many constraints. If we have to wait 15 years for an approval, it's not suitable for our business right now.
Thanks, Alex. Do we have any other questions in the room? Maybe you just mentioned that it won't be Europe, it will not be the United States, but there could be others. Do you have at the moment any countries or places that might be the first, in your opinion?
Just, of course, and we have very specific location, which I prefer not to disclose here, but basically you need always a big city and secondary cities that are between 200 and 500 kilometers away or something like that. That gives you an excellent business case for the Hyperloop. We have also many other configurations, and also with when you take into account cargo, but this gives you an idea where you can find this application. And the northern part of Africa, the Middle East, and some other places are very suitable for that.
And I think I missed it during the presentation, but do you have an inkling at the moment to what max speeds you're looking at?
Yes, so the physics tells you, or the engineers tells you that you can optimize the design for below 1200 kilometers per hour roughly, or above speed of sound. Above speed of sound, you nearly have no application on the planet Earth. So we go below. We think we will end up between 600 and 1000 kilometers per hour. It's both what is very reasonable to do. It makes it very competitive, and yeah, and the problem with the higher speed is you just cannot afford for the cost of having a near straight line. So you always have curves in all the directions, and too much of a high speed cost too much at some point.
Well, look, it's still super fast. I just wonder, are there any implications for us as human beings traveling at that speed? Or is the fact that it's enclosed mean that there is no frame of reference, so we cannot, perceive how fast we're traveling?
So we use the same values than you find in an aircraft or in a railway or in a car, except, of course, for the sport car. But this is given by the human body, so this is very well known. And we look at acceleration ideally of 0.1 g. So if you, so it's a very smooth acceleration. In an aircraft, you're traveling at above 900 kilometers per hour, and you have a smooth experience usually. So this is what we are looking at. We can go higher acceleration, but we will stay in the same ranges that are very known.
Thanks, Alex. I have a question from somebody in the front here.
How are you thinking about solving that last mile problem? Are we gonna see like a network of those, or is it really gonna be just two end-to-end cities which have a lot of traffic between them? Like, do you even care about how people then get to these endpoints a bit from further away, or will you focus on those high impact points for the foreseeable future?
It's a very good question, and we have identified this as a strategic point to solve. And since the beginning, we have always considered door-to-door travel. So that's the, and we have an excellent, of course we are excellent in everything, but now we are really excellent in our, I think, passenger experience. Here, a lot of work has been done, taking into account the A to B. On a more practical level, there is no Hyperloop if you have a station in the middle of nowhere. Okay, Hyperloop will exist just if it's interconnected, intermodal. So if you arrive in the city, one of the main issue with an airport is you need a lot of area. So you need to place it outside the city, and this is what makes many big airports not so usable for many travelers. And it will be the same for the Hyperloop. We need to arrive in the city centers and then be interconnected with the local modes of transportation. But this is a this has an impact on our design, because we need to have stations that can be implemented in many different situations. After, it's a question of city planning.
Hi, Alex. You mentioned safety quite a bit through your presentation. I think the World Health Organization claims that 1.3 million people currently die in traffic deaths a year, which is obviously a huge figure. It seems interesting to me that every time a Tesla crashes in autopilot mode, it's headline news, but no one really talks about the number of lives that may be saving on a daily basis. It's actually quite a morbid question, but do you have like North Star metrics to reduce those numbers? I imagine introducing a new form of mobility system is a risk, but are there ways you can kind of guarantee those sorts of numbers are reduced, or is there kind of proof you can have at the moment to introduce that reduction?
So this is our I would say not only goal, or it's our main focus. So you have two things, okay? You have we won't be reducing accidents happening by car or railway or other modes, just for the fact that we are not really in competition. What we have seen in the feasibility studies we did is that we are an additional system enriching the mobility solutions for the passengers, but we are not replacing a route of an airline or a railway connection or these kind of things, or route. Of course, you always have some intersections, that's yes, but it's not frontal. So it's not because you're installing a Hyperloop that will be safe, that you will solve safety issues on the roads, because it addresses different needs. The way we demonstrate it is very standardized. Also here we are not trying innovating in any way. We are using what the aerospace and the airlines, especially with the aerospace did, and the railway did very successfully, is you have a framework defined by the governments that sets targets that you have to meet, and those targets, as we progress, are always higher. So the newer systems that are developed are more safe, just because the targets are raised. Today, you probably will never be allowed to develop a motorbike, for example. Having someone driving at such high speeds with so little protection, we could not develop it today. It's existing because it's been developed earlier, where the safety targets were lower. And so this approach is what we call the certification approach. It's 80% of our activity is to demonstrate that our safety system is safe in any case. In any case, we always need to bring out people safe, even if you are fire, if you are stuck somewhere, if you hit something, if you have a hole in the tube or in the capsule. And so this is what we do in our daily activity. Not sure I fully replied to your question. Yes, okay.
Okay, Alex, thank you very much for your presentation and good luck with this excitingly fast project. Everybody give a big round of applause to Alex Zisa.